It's been a while since I talked about the Tardis control synth, and to be honest, I've been kind of busy with other projects, general apathy, and work, I guess. But stuff has happened. The arpeggiator that I built in the last video is now installed, but in doing so I discovered that the plastic that this is made out of is an absolute bastard to drill. So I'm looking at other ways of attaching things to this. I have attached the Atari Punk console from the Mumno computer that's now stuck onto the top layer. What else have I made? Well, I said I wasn't going to use a bipolar synth power supply because it seemed like extra effort, but actually I've been convinced by various people that, it does make sense. So I made this from a kit. This is a synth power supply. What this does is it takes 12 volts AC from an AC adapter and it splits it out into a positive rail plus 12 volts and a negative rail minus 12 volts. And that's really good because things like operational amplifiers are differential amplifiers and they work off having a difference. So they need positive and negative voltages. The slight complication is I've already built some modules that run off 5 volts, 9 volts into a 5 volt regulator. So I don't know if having two power supplies on this is going to cause weird ground loop issues, but we'll figure that out. Okay, this is something weird. It's a ghost detector. Now, I decided I wanted to make a ghost detector, and the way they work is we are surrounded by electromagnetic radiation all the time, and it's really low level. But if you build in enough amplification, you can amplify that EM field and make it register on a meter, and that's all a ghost detector is, broadly. Now, I saw a design online and I didn't think it would work, and I modelled it in a simulator and I still didn't think it would work, so I designed my own. And this didn't work in the simulator either, but I was really sad one day and felt like soldering something, so I made it anyway. And what it's supposed to do is it has cascaded transistors. Now, transistors can act as an amplifier, so if you cascade a couple together, then you're getting the product of those amplifications. I knew it wouldn't work. It didn't work in the simulator. It doesn't really work in real life, but what it does do is generate interesting noise, so I might actually stick it on the synth as a noise generator. I wasn't deterred from my ghost detector ideas, so I also made this, which looks quite cool. This is an arduino-based ghost detector. It's exactly the same principle. The code is very bad, but what it does is when EM currents hit this antenna, they're red on one of the input pins, and then that's massively boosted. And after it's boosted, depending on how strong it is, it lights up these LEDs to give you an idea of how strong that signal is that it's detecting. It's not a synth. It doesn't make noises. I actually wanted to make noises, but I couldn't get that to work. It's just a way of adding some flashy lights to the synth. What else? This was made for another project. This is one of those fuzz for a fiver circuits, and I was going to put it in another project that got postponed. So I've cut it out and I've kept it. I'll put it in this because super simple, super quick to make, but actually sound really good, and they're a very pleasant distortion. So this will be going into my synth at some point. What I said was, having made the arpeggiator, what I really needed was a bunch of oscillators, because a synthesizer is based around a bunch of oscillators, and instead of doing the sensible thing and just getting on with it and building them, because what I wanted to do was compare arduino-based, transistor-based, and I think op-amp-based. So I had an idea I was going to compare these three different oscillator types and use them all in the synth. Unfortunately, I got sidetracked with this monstrosity, and I decided what I really wanted to do was build one of my oscillators into the Pomsie, and I'm partway there. It has a pot which controls frequency, or it will do when it's connected up, a pot that controls CV, switches that control the waveform shape, so you can have sine wave, square wave, or triangle. And this is my favourite thing, there's a switch hidden in the horn which controls whether it's an LFO, low frequency oscillator, or a VCO, a voltage controlled oscillator. And the fact that it's in the horn just gives me delight, pure delight. I know, I'm a genius. What was I saying? Oh yeah, so inside this it's just the switches wired up at the moment. This is its brain. Now I prototyped this oscillator before I started this build. I prototyped it a while back, so I'll show you a video of that. So this is based on Hajuo's arduino-based VCO LFO, but I couldn't get his code to work, so I've written my own code from scratch, which is very simple. It uses a library that's made for this specific breakout board, which is a board that's designed as a test oscillator, so it can put out different waveforms. The code is really simple. What it's doing at the moment is it's in LFO mode. So we've got a triangle wave that's at quite a low frequency. So at the moment it's 11 Hertz. And if I turn the pot, that frequency is increasing. And I'll talk through the code in a sec. It's very simple. You can also change the shape of the waveform. So what I've done is the equivalent of flicking a switch. I've just pulled apart two cables which were taking this pin input to ground, so now the pin input has gone high and the waveform shape has changed. So that's your sine wave LFO, and if I unplug the other equivalent switch, if I can get that to look nice, we now have a sort of square wave. Our scope is very slow. You see it's a little bit on the wonk. That looks like there's a bit of a capacitance issue maybe, but broadly it's a square wave. Okay, what other switches do we have? Okay, so this is flicking the switch that's the equivalent of changing between LFO and VFO, so we're now into audible frequencies. Okay, so now we have a square wave that's running at almost 4K. And now a sine wave that's running at almost 4K. So you can see this is quite flexible and it's relatively easy to make. What I'm going to need to do next is make an amplifier, because one of the limitations of this is it's putting out really tiny voltages. Again, this is something that Hajuo addressed in their tutorial. They used an op-amp-based amplifier. I've not looked into that yet, but that'll be the next step. So this is another version of my Arduino oscillator. What I did was I rebuilt it onto a Nano, so this is the version that's actually going to fit inside the Pomsie and be its brain and do its noise making. At the moment it's putting out 5K sine wave and it's working. What complicated this project was, for some reason, the code that worked fine on the bigger Arduino didn't work on the Nano, so I ended up finding a different library and having to rewrite the code, and that took a bit of time. In the meantime, while I was testing, I managed to fry an Arduino, so this is actually the second build of this, because the first one, she died. Yeah, so it's the same as the previous. If I can just find a cable, if I short one of these pins to ground, the waveform's changing, so now it's going from the sine wave into a square wave. Okay, so what's happening now is you see the scope's gone a bit mad. The pin 7 on here controls whether this works as an LFO, low frequency oscillator, or a VFO, a voltage controlled oscillator. And the LFO maximum frequency is 20 Hertz. And I don't actually have the pot connected yet, which controls the frequency that is actually inside the Pomsie, so it's not wired up. So what that means is this is wavering around 20, actually just below 20 Hertz, and the scope doesn't like that. But what I can do is, if I short pin 7, this is the one that the LFO VFO switch comes off. So if I short that to ground, it switches into being a VCO rather than LFO, and suddenly we have a waveform that we can see because it's jumped up to 5K, which is
the top of the range at the moment for the VCO, and that's all changeable. It's all changeable in the code. So LFO, and if I do the equivalent of closing a switch to ground, VCO. When I originally decided to make an oscillator based on Arduino, I thought I would end up using what's called a wavetable method. And what that means is you end up storing amplitude values that describe the waveforms that you want to hear. You store them on your computer chip, and when you want to hear that waveform, you read the values back. And the way you change frequency is by reading the values more quickly or more slowly. So that's a lookup table describing wave shapes. I did some research and I discovered that Haduo was using this AD9833 breakout board, and this is actually a small function generator. So this itself makes the waveform shapes. So all I have to do is use the library in Arduino that says, please give me a sine wave at this frequency, please give me a triangle wave at this frequency. So this has actually massively simplified the build. However, it did take me a long time to find a library that I understood, because I'm not amazing at programming, and that also that worked for me. So I end up writing the code from scratch. So this is my code. It uses libraries that have these inbuilt commands, which makes it simple. The complication for me is all the communication is done via SPI, which is something I'm not super familiar with, but it's just a language that lets the Arduino talk to peripherals. So you have a bunch of pins that you define on the Arduino, and they connect to pins on, in this case, the board that's doing the signal generation. And that uses standard pins, but for safety, I've defined them here anyway. So I just set up a bunch of variables. I set some pins on the Arduino to high, to 5 volts, and that Y will become apparent later in the code. And then what I do is I get the code to read those pins, and it reads whether they're set at 5 volts or 0. And they'll be set at 0 if I flick a switch that pulls them down to ground. And the reason you can do that is these pins internally have a resistor on them, so it's safe to pull them down to ground. You won't pull too much current and short circuit your Arduino. And depending on which switches are flipped, you'll either get a sine wave, a square wave, or a triangle, depending on whether you get 1s or 0 at those pins. The third switch controls whether we go up to 20 Hz or 5 kHz, and that's depending on whether we want the oscillator to act as an LFO or a VCO. And of course, this is very easy to change in the code if I decide that I don't like these frequency limits. Where that resistor is currently not connected to anything, that will be connected to one of the pots that's in the Pomsie's eye at the moment, and that will read a value from 0 to 1023, because that's the range that Arduinos read. And what I'm doing is I'm telling it to map 0 to 1023 over the range of frequencies that I want. So if I want to go up to 20 Hz, I will read a voltage and I will map that between 0 and 20. And likewise, if I want to go up to 5K, I'll read a value and that will be mapped between 0 and 5K. And then the last command in here just sends that frequency to the device. The one drawback of using this breakout board is it actually puts out a really small amplitude. It's putting out like millivolts, hundreds of millivolts rather than volts. So the reason there's a bunch of space on the board is that I'm going to need to add in an operational amplifier to bring that signal up to something that will work with my synthesizer. Hopefully in the space on the board I'll also have a Vactrol. What that is an LED coming off the CV input pot that's connected to a light dependent resistor. So what that'll do is it'll decouple my synthesizer that's giving this a signal from the circuitry here, so I can't accidentally blow up my synth. But as the voltage coming in changes, we'll get a flashing light, and that'll control the CV current that's going into this. I'll show you that. I'll show you that when I actually make it. So that's it from us. I will give you an update as soon as I can, but realistically it's going to be about 3 months now because I'm not going to be here. Say goodbye.